Welcome to the 2024 season of the Astrophiz podcasts. My name is Brendan O'Brien, and first of all, we would like to acknowledge Australia's first astronomers, the Aboriginal and Torres Strait Islander people, the traditional owners and custodians of the land we are on. This episode is produced on Yorta Yorta country, and we'd also like you to influence your local politicians to do more to mitigate climate change by moving from fossil fuels to renewable energy sources. We're now in our 9th year of production with over 180 fabulous interviews with top scientists from all over the world. Each month we produce 2 fabulous episodes. On the first of each month, Dr. Ian Astroblog Musgrave gives us his monthly Sky Guide, plus a unique astrophotography challenge. Then, on the 15th of each month, we publish an interview with a leading astronomer, astrophysicist, space scientist, data scientist, telescope engineer, project manager, or particle physicist, and we discover their science journey and rare insights into how they think and conduct their amazing research into exactly how our universe works. Our audio files and transcripts are available on our website at astrophiz.com, and MP3s can be freely streamed from SoundCloud and Apple Podcasts. Today we have a sensational interview for you from Denmark with Dr. Hannah Diamond Lowe, who uses the world's newest and most powerful instruments to probe the atmospheres of distant alien planets. You'll love her stories. Hello, Hannah.
Hello, Brendan.
Today, listeners, we're zooming over 10 time zones to Chile, Denmark, for some cutting-edge science, and you're invited to a very special conversation. So today, I'm lucky enough to introduce you to Dr. Hannah Diamond Lowe, who is a senior researcher in the Exoplanet group at the National Space Institute, the Technical University of Denmark, where her groundbreaking research characterizes small exoplanet atmospheres using ground and space-based observatories. She is also the principal investigator of the Hot Rock Survey, a large observing program using the now legendary James Webb Space Telescope to test terrestrial rocky exoplanets for their atmospheres as they orbit nearby M-dwarf stars. As well as she's got a companion program called Hot Rock Stars, which will measure the UV output of the M-dwarf hosts with Hubble data. These are the best project names I've ever heard, Hannah. So thanks very much for speaking with us today.
Oh, thank you so much for having me. It's fun to be here.
Okay, thanks. So before we talk about your current exoplanet work, can you tell us where you grew up, please, Hannah? And could you tell us how you first became interested in science and space?
Yeah, definitely. So I am born and raised in New Jersey on the East Coast of the United States. And I'm kind of from the middle of the state in a town called Highland Park. So the area is a sort of kind of like dense suburbia. So I'm not actually one of those astronomers who did a lot of gazing up at the sky since, there's a good bit of light pollution. I didn't really get into science and space until sort of later in my schooling, but my dad has always been quite interested in astronomy. So like for Hanukkah one year, I got a telescope and we would sort of look at the moon and Saturn, and I was into that for a while and then kind of dropped it. But I think he was kind of laying the groundwork for some astronomy later on.
Okay. And what about those early school days and your earliest ambitions? And did your early ambitions change and evolve over time, Hannah?
Yes, there was a lot of changes and evolution. So yeah, as I mentioned, there was like a small phase of my childhood of wanting to be an astronomer, but There was also, I wanted to be an archaeologist, a political scientist. I think at one point a librarian was high on the list. So I really kind of jumped around a lot. But I think like generally, I just always liked school and learning. And my favorite subjects were just the ones where I really liked the teachers. So at different points, I really liked English, math, history. And even all through high school, I kind of jumped around a bit. But I didn't get into actually sort of focusing on science until I went for my undergraduate degree at the University of Chicago. In the US, we do this liberal arts education. So you have to take like a broad range of subjects, everything from math and science to history and literature. And then you choose something to major in and sort of study more in depth. So I went into college kind of thinking about maybe like I'd focus in anthropology or maybe linguistics, but definitely I was thinking something in the humanities. So at the end of my first year, I decided to do this study abroad program. And while I was studying abroad, I could take a course in astrophysics for non-majors. So I could get my kind of obligatory science credit out of the way, and I got to spend a quarter in Paris. So Paris was great, but I also really, really enjoyed the non-major astrophysics course. So after that, I kind of decided to start shifting more over into the sciences. But I didn't actually major in physics because at that point, there wasn't enough time for me to graduate in time and take all of the physics requirements. Plus, it was like a lot of physics. So I actually majored in geophysical sciences so I could take sort of a more diverse range of science courses. So I took geology, biology, biodiversity, but I did take a lot of sort of requirements in the physics department and in the astronomy department as well. So yeah, then the rest is sort of history. I got more and more into research and astronomy, and then kind of that just sort of kept trending in that direction eventually.
You must have had some inspiring teachers and lecturers here, and
absolutely.
Not only did you get your first bachelor's science degree in geophysical sciences, you did it with honours at the University of Chicago, and then you went east to Harvard for your 5-year PhD in astronomy. Now, for our early career researchers, we know we've got some listeners who are in that category. Could you tell us how you arranged it? And firstly, why you made that big move over to Europe to take up your first postdoc position at the Department of Space Research and Space Technology at Danmarks Tekniske University, the Technical University of Denmark. How and why did you do that, Hannah?
Well, firstly, excellent Danish pronunciation, I must say. Yeah, so there were a lot of reasons why, that some sort of overlapping and some just kind of, it sort of came together. I think it might be easier first to answer more the how, since that was kind of straightforward. So, in the last year of a PhD, if you're going to continue in academia, that's when you typically kind of start applying for postdoc positions. And I was very unsure about sort of where I stood kind of compared to other graduate students. So I applied to a lot of postdoc positions. I think it was like 30. And I think that's too many, since a few of those I applied to, I didn't, weren't actually good fits for me. But kind of in the mix there was this position at DTU Space, since they were looking for someone in exoplanet research that focused on small planets. So I sort of thought, okay, well, throw that in the mix. So I had all these applications, but more into the why, I did have some idea that I wanted to go to Europe for a postdoc. I did a lot of my PhD in ground-based astronomy, and Europe has some of the best ground-based telescopes and instruments, but they're also building the next generation of giant ground-based telescopes. And this is happening in the US as well, but Europe is going to get there first.
Yep, cool.
So, at the time I was applying for a postdoc, this was the end of 2019, the launch of the James Webb Space Telescope was supposed to happen at the beginning of my PhD and had not happened at all. So I was kind of thinking, well, I don't want to rely on this space telescope to launch if the timing is not going to work out for the 3-year PhD. So I sort of focused my postdoc applications on ground-based research. And that was, much easier to do for sort of the European postdocs I applied to. But I'll be honest, another reason was that I just kind of wanted to have a change of pace and have a different sort of life experience. So I'm half British, and I grew up spending a lot of time in the UK. And I always had this kind of interest of like, oh, maybe I could, move to Europe at some point. But it didn't happen for my PhD, obviously. So I thought, okay, maybe a postdoc was a good kind of opportunity to try that. And really, I'll be honest, even though I had a strong kind of academic like pedigree, University of Chicago and going to Harvard, I was really burned out by the end of my PhD, and I was not feeling very strongly about wanting to stay in academia. I mean, I really liked astronomy and I really liked the questions, but the career of an astronomer is not always just getting to do the fun sciencey parts. So I thought, well, if I'm not going to make it long term, I might as well check off some life goals. And actually having that little bit of pressure off, sort of being at maybe not sort of the most prestigious position I could be at, and having a better work-life balance really led me back to enjoying more, actually going to work, doing the sort of nitty-gritty stuff you have to do. So I'm really glad I ended up where I did, but it was not such a clear path forward all the time.
Fantastic. A great combination of strategic thinking, adventurism. As we'll find out a bit later, you landed in the perfect place for the research you're doing at the moment. Okay.
Absolutely.
Look, today, the plan is to go back to the early exoplanet atmosphere science, then have a quick look at your PhD, then hear about your latest discoveries and projects. But first, for our listeners, could we get the big picture on exoplanet atmosphere science, please, Hannah? What have been the big milestones since 2001? It's a science that's been only alive for 23 years, when a Hubble spectrum showed that sodium was present in the atmosphere of HD 2094-58b. Now, that's quite a mouthful. And just before you answer that question about the big milestones, can you tell us, do you give nicknames to your target exoplanets, Hannah?
So I don't typically give like nicknames for the planets, but the one you specifically just mentioned, HD 209458b, that is one of the most famous planets in exoplanet studies. So people have looked at this for years and years and years. So that one people will definitely shorten to HD 209 or even just 209. Sometimes you just take the first three numbers. But I'll try to avoid throwing out too many planet numbers because they can get a bit of a mouthful. But if you do want a slightly sort of easier way to think about them, because it does sort of seem a random assortment of letters and numbers, the HD part of HD 209 actually stands for Henry Draper, who was an astronomer in the 1800s who made this like catalog. And so this star was the 209,485th star in that catalog.
Wow.
But Henry Draper in the 1800s would have had no idea that this particular star had a planet and that this would become actually a famous planet for exoplanet atmospheres. Anyway, but sorry, back to the big picture. Yeah, in many ways, we're still sort of painting the big picture of exoplanet atmospheres because it's, as you said, just such a young field. But this was a major milestone. So in 2001, sodium was detected in HD 209's atmosphere. And that paper was led by Dave Charbonneau, who was actually my PhD advisor.
Wow.
And yeah, shoulders of giants. Yeah, so this was a milestone both for exoplanet science and also demonstrating the kind of techniques we would use to pursue discoveries. So this particular one was transmission spectroscopy. I think you've had a few folks on the podcast talk about transits.
Yep.
So a transit is when a planet passes in front of its host star from our perspective. And if you make the same observation, but with a spectrograph that spreads out the incoming photons based on their wavelength, you can then get a spectrum of the transit, or we would say a transmission spectrum. And what that's doing is that light from the host star will filter through the planet's atmosphere on the way to our telescopes. And any molecules present in the exoplanet's atmosphere will block light at wavelengths specific to that molecule. And it'll make the planet look larger at those wavelengths and ultimately give us a sort of spectral fingerprint of those molecules.
Yep.
So for a long time, transmission spectroscopy was only possible for hot Jupiters, which are just as they sound. They are planets the size and mass of Jupiter, but orbiting much, much closer to their stars, actually closer to their host stars than Mercury is to our own sun.
Yep.
So very tight orbits. And these hot Jupiters have extended, puffy atmospheres that lend themselves well to the technique of transmission spectroscopy. So in this way, we're detecting a host of molecules in hot Jupiters, carbon dioxide, carbon monoxide in some cases. And we could sort of attempt to determine maybe where those planets formed in the disk as they migrated to their current position where we see them now.
Yep.
So from there, the observation techniques have expanded as well as the science. So you can also take an emission spectrum, which is like a transmission spectrum, except you watch as the planet passes behind its host star and you try to detect some thermal emissions, some photons from the infrared.
Oh.
And we've also done phase curves. So that's when you actually watch the whole orbit, and that gives you a wealth of information. And as these techniques have evolved and we've built bigger telescopes and more stable and more sensitive instruments, we've pushed to smaller and smaller planets. So a couple of key milestones were detecting molecules in the atmospheres of sub-Neptunes, which are planets a little bit larger and more massive than the Earth, but also still relatively puffy, so we can still access their atmospheres. We've detected things like water and methane in sub-Neptunes, and we've also detected like flat, featureless transmission spectra, and we think this is the result of clouds or hazes in those planet atmospheres. And I would say the last part of the big picture, which is very much still, being painted, if you will, is like pushing down to even smaller planets, planets that are sort of more terrestrial in nature.
Fantastic. That's so cool. Okay. We've got the big picture now. We're standing on the shoulders of giants. Now, can we have a quick look back at your PhD research to help us understand your personal research trajectory? You focused on the atmospheres of terrestrial exoplanets using ground-based optical transits and the UV output of M-dwarf host stars using space-based UV spectra. Now, what big questions were you asking and what problems were you working on then that you had to overcome to get your PhD?
Yeah, so that's a great question. So my PhD ended up kind of having these two pillars, which was using the ground-based telescopes to try to observe terrestrial exoplanet atmospheres, and then using Hubble to try to get UV spectra of their host stars. The UV bit didn't really come till the end of the PhD, so I'll mostly focus on the first part, the ground-based telescopes, since I think I'll talk a little bit more about the UV bit later. So I knew from the beginning of grad school that I wanted to do exoplanet research, and I had this undergraduate background in geophysical sciences. So I really wanted to be thinking about smaller, more terrestrial-like planets. The problem was that when I started graduate school, so this would have been the fall of 2015, there were no terrestrial exoplanets that were close enough to us and also transiting so that we could actually study their atmospheres. We detected plenty with Kepler, but the Kepler terrestrial planets are too far away for us to do atmospheric follow-up.
Yeah.
But luckily, in one of very first meetings with my PhD advisor, he told me that his former student, Zach Berta Thompson, who's now a professor at University of Colorado Boulder, Zach had just discovered exactly this kind of nearby Earth-sized planet transiting a nearby star that we could actually look at for some atmospheric follow-up. So basically, as soon as I got to Harvard, I applied for time to use these telescopes that Harvard is a partner in, called the Magellan telescopes. These are 6.5-meter twin telescopes at the Las Campanas Observatory in Chile. So I applied for time to use a little spectrograph on one of these telescopes, and I got it. So I was able to travel down there and observe some of the sort of early transits of this planet that had just been discovered. So this planet was GJ 1132b. Sorry for no fun nickname. But I was able to get a transmission spectrum of this nearby planet, and it was completely flat, so not a lot of evidence for an atmosphere. But given the telescope and instrument, we were only really sensitive to relatively puffy atmospheres. So the flat transmission spectrum was basically telling us that we already knew the planet was similar to the Earth in terms of size and mass. It might also be similar to Earth in terms of having a sort of thin atmosphere tightly packed to the surface. Or it could have been a bare rock, or maybe have some weird high clouds. But this was basically the state of the art of what was possible at the time. So as a few more kind of terrestrial exoplanets got discovered that were nearby, I would go off down to Chile and try to get observations with Magellan. And basically, I just kept reporting flat lines for my whole PhD.
Ouch.
Yeah. But getting to travel to Chile and use these amazing telescopes and be a part of that observing community on the mountain was one of the really kind of great treasures of my PhD experience. I absolutely loved it. And then the aftermath of toiling away on analyzing this sort of very noisy ground-based data, looking for tiny, tiny signals that we were, would barely be sensitive to. That was tough. And especially, by your third or fourth flat line, it just kind of feels like you're not really doing that kind of groundbreaking research you dream of, when you kind of go into a PhD. So definitely some highs and lows in that process.
Oh. I think it's everyone's dream to do some observations at Paranal.
So this is actually not Paranal. That's the mountain over. This is a smaller observatory, but it's a very similar location, and yeah.
Yep.
But yeah.
Okay, so that brings us up to date. Do you want to mention what might be the very latest techniques and technologies that you're using to interrogate the atmospheres of exoplanets? You've hinted at them already. What's exciting for exoplanet atmosphere scientists right now, Hannah?
Yeah, I think 4 words, right? James Webb Space Telescope.
Yeah.
It's really just opened so many doors and given us access to planets we haven't been able to study before, and also parts of the sort of electromagnetic spectrum we haven't had access to at the precision that James Webb can deliver. I'll try to be a little more detailed about that. I'll actually give an example. One of the early sort of releases from JWST was a transmission spectrum of a sort of hot Jupiter we'd known about for a long time called, here comes another boring name, WASP-39b. And we had observed this planet before with Spitzer, which was a telescope that's now been decommissioned, but we had access to these infrared channels, but they're just this big sort of photometric bucket. So you're just putting all your light into this big bucket. There's not a lot of spectral information. And just from 2 big light buckets that Spitzer had, these 2 photometric band passes, there had been hints of that maybe this planet had carbon dioxide. But, it was just a hint that you can never tell anything more than that from Spitzer. We took one look with JWST. I think it was just one transit. And you could just see this beautiful, clear feature of carbon dioxide. You don't need to go and dig into your models and do some fancy cross correlation. It's just right there. It's just glaring you in the face.
Wow.
Boom, carbon dioxide.
Cool.
So that was beautiful to see. But even in this kind of, this was just supposed to be a demonstration of what James Webb could do, there was actually this second little bump kind of right next to the big CO2 feature we were seeing. And it was like, well, what is this? Like, we weren't expecting this extra little bump. And what people think now is that this is actually the first detection of sulfur dioxide, SO2, in the atmosphere of an exoplanet. And not only is it, it's fun to detect a new molecule, but what does that mean? And we're actually seeing this as evidence of photochemistry occurring in the atmosphere of an exoplanet, which has we've never seen evidence of that before, even though we kind of think it should happen. So all that means is that sulfur dioxide is very easily broken apart by high energy photons coming from this planet's host star. So we shouldn't really be seeing it in the atmosphere. But if we are seeing it, it means there must be a sort of continual cycling of the molecule being broken, going through some chemical pathways, and then being reformed. This is a process that happens on Earth. It happens on Venus. So, for example, we have oxygen in Earth's atmosphere. Photons from the sun break apart that oxygen and allow ozone to form, which is, of course, very important for us here on Earth. But just that process of photochemistry that is occurring, we've now also seen it occurring in an exoplanet. So this was just kind of like a mind-blowing, bonus we were not expecting at all. And I think kind of all these early observations and probably for a long time are going to have these kind of exciting things. We're going to look for one thing and end up finding something else or something we weren't expecting.
Fantastic. And I asked you what's exciting, and the timbre in your voice is conveying that excitement very well. Okay, look, let's do M-Stars 101. I did a search on the archive server and found a paper you worked on which focused on M-stars. What are M-type stars and why are they the focus of your work?
Yeah, so going into Exoplanet, my sort of PhD in exoplanets, I did not think I would spend so much time with M-stars, but I'm so glad I did. So an M-star, or we sometimes say an M-dwarf, which just means it's still on the stellar main sequence. It's a star, like the sun is a star. It fuses hydrogen in its core, but it is smaller and less massive. So M-dwarfs can be about 20 to 60% the radius and mass of the sun. And they're also typically much cooler. So the sun is around 5,500 Kelvin. An M-dwarf will have a sort of effective temperature of around 3,000 Kelvin, or a little bit cooler, a little bit warmer.
Yep, okay.
M-dwarfs have a few advantages if you're interested in studying small planets, and this is sometimes referred to as the M-dwarf opportunity. And those advantages are, they, as I said, are smaller. So if you're looking for a transit, you're looking for the relative size in the planet to the star. If your star is smaller, that relative size of planet to star goes up compared to if you're looking for a small planet around a much bigger star. So that's an advantage. M-dwarfs are also much more numerous. So the solar neighborhood is actually about 75% M-dwarfs. There's not so many sun-like stars compared to M-dwarfs. So you have more opportunities to actually find transiting planets and be able to study them. And finally, because M-dwarfs are cooler, their quote-unquote habitable zones reside kind of closer in. So if you are interested in looking for temperate terrestrial planets and studying them, a sort of temperate planet around an M-dwarf might be on an orbit of about 25 days. Now that's still pretty tough to observe, only one opportunity a month. But compare that to an Earth-like planet around a sun-like star in the habitable zone, that only goes around once a year. So the 25 days actually looks a lot better. So this is sort of why M-dwarfs are targets if you are wanting to study terrestrial-like planets. But they have a few drawbacks, which have been really fun to learn about. So an M-dwarf is not just a sort of shrunken down sun. They actually have pretty different evolutionary histories. M-dwarfs are active for much longer timescales than a sun-like star. And they, even in their sort of middle age on the main sequence, they actually have very different looking spectral energy distribution. So compared to sun-like stars, M-dwarfs emit much more flux in the ultraviolet and extreme ultraviolet than sun-like counterparts. And that's important for my work because if you're trying to detect an atmosphere around a terrestrial-like planet, you are, of course, most sensitive to the very outer regions of that atmosphere because, that will have more chance for light to pass through it. But also those outer regions are more susceptible to the high energy flux from the host M-dwarf star that actually gets deposited in the upper atmospheric regions. So it doesn't get down to the surface. It actually gets absorbed in the outer regions of a potential planet atmosphere. So if you don't know what that star is depositing onto the exoplanet's atmosphere, you might not truly understand what you're seeing, whether or not it is an atmosphere with certain molecules. Maybe the planet has no atmosphere. You're not going to get the full picture unless you understand what the host M-dwarf is doing. So that's why I've sort of tried to bring M-dwarfs into my research and tried to kind of combine understanding M-dwarfs in the UV with trying to characterize the atmospheres of terrestrial exoplanets.
Fantastic.
Great.
That makes so much sense. Awesome. Okay. Look, Thank you, Hannah. Now, there's another 15 papers you've worked on up on the archive server. And as you've mentioned, you've used data from Spitzer and Hubble. You've also used Chandra X-ray data to look at those hot Jupiters and the hot Neptunes and triple star systems. You've been very busy, but your most recent work, obviously, as you've mentioned, is all about rocky terrestrial exoplanets. Now, there's two parts to this question, Hannah.
Okay.
Are you looking specifically for Earth 2.0 and for specific biosignatures? And this is a big one, could you tell us about your PI work and the Hot Rocks project and but securing observation time with the MIRI instrument on the JWST? That is so cool. Now, Hot Rocks looks both ambitious and achievable, and it sounds absolutely fantastic. Your team must be over the moon with this one. What are they up to right now, and when can we expect your atmospheric analyses of the targets you've selected? When can we expect them to be published? Now, what's the timeline, Hannah?
Yeah, okay. Big question. To start with the Earth 2.0 question, I'm going to try to make like a metaphor here. So I think that looking for Earth 2.0 is like looking for buried treasure.
Yep.
So it's incredibly exciting to think about. And I think this is, the direction we're moving as a field to try to look for Earth-like planets around sun-like stars and try to determine if they have atmospheres or other properties similar to our own. But just as with buried treasure, it might not be, might not end up being everything you dreamed of and all the gold and jewels. We also have to be aware that we might not actually find something that looks exactly like an Earth 2.0. And so we can either sort of relax what we think of as an Earth analog. But even more importantly, back to my buried treasure metaphor, isn't it just as much about the journey and the adventure and, the friends you make along the way? So on the way to actually developing the capability to look for and detect an Earth 2.0, we're finding so many incredible planets, and we're only just beginning to be able to characterize those atmospheres.
Yep.
So I don't sort of wake up every day thinking about Earth 2.0. Maybe I would say I actually spend more time thinking about like Venus 2.0, since typically the terrestrial planets we have access to are hotter than the Earth.
Yep.
So for me, it's more about like there is so much to learn about exoplanets and so much just to learn about planets in general, populations, atmospheres, and thinking about where our own solar system fits into that is still a very open question. We still we can maybe access some sort of Venus-like planets, hotter planets orbiting near M-dwarf stars. But what about cooler planets, planets out to where like Neptune is? What about the moons of those planets? So there's so much sort of discovery space that I think is worth exploring. And if we only just try to go straight for Earth 2.0, we're going to miss a lot of really interesting science that I think ultimately will help us more to get there in the future. Yeah. So sort of one of these adventures along the way that I'm working towards is to ask whether or not terrestrial worlds around M-dwarfs can even have atmospheres at all. So when I sort of talked a little bit about M-dwarfs, they have these very different histories. They have much more high energy output. And this stuff can be damaging for exoplanet atmospheres. So there's been a sort of, question for a long time, like, yeah, these stars present really exciting opportunities for detecting terrestrial exoplanets. But does it stop there? Are those planets just barren rocks? And if they are, that's also interesting because then you can study their surfaces and what those look like. But in the Hot Rock Survey, we want to go after the low-hanging fruit. So these are terrestrial worlds orbiting very close to their M-dwarf host stars, and those M-dwarfs are in turn close to us, so we get more photons from them. So this is important because even though I've talked a lot about transmission spectroscopy, the Hot Rock Survey is doing like the opposite of that. We're going back to basics. We are watching these planets in secondary eclipse, so when they pass behind their host stars, so like the opposite of a transit. And we're using the MIRI instrument on JWST as a photometer, so as a big photon bucket out at 15 microns, so well into the infrared. So we're actually not getting spectra at all. We're just getting one big data point out at 15 microns. And we do this because with the photon bucket, you just can collect many, many more photons. And the secondary eclipse signal, so the kind of, you can think of the transit dip, it's kind of the same thing in secondary eclipse, but much, much shallower. So you're looking for this tiny signal. You need as many photons as you can get. And the point of all of this is not so much to characterize an atmosphere, but to ask whether or not an atmosphere is even present on these planets. So that's the main kind of goal of the Hot Rock Survey. I will say to get the time to do this on James Webb is incredibly competitive, and you need a lot of luck just to get it also. So it was a lot of hard work by myself, my co-PI, Joao Mendonça, and also the whole team sort of like thinking about this question early on. So it was a lot of work and a lot of luck to get that time. And if you are out there and you have applied for time on James Webb and, like me, been rejected many times, keep trying. It will happen at some point. Yeah, so where we are right now with the survey is we're just at the beginning. So we only got our first observation at the end of November. For the 9 planets in the survey, for most of them, we actually have to stack together multiple observations. So even though we got one observation, we might be waiting for a second observation. And the way the James Webb scheduling works, you don't have much control over that. So we don't have any completed data sets yet, but we are currently in the sort of data collection phase, and that is also coming with a lot of preliminary analysis and a lot of hard work trying to build up these pipelines, these codes to analyze the data, to be able to do the best we could do to try to pull out this tiny, tiny signal. And I am so lucky to have a really great team of international researchers who are really excited about this work. So as I said, we have 9 planets in the survey, and each planet has what we're calling like a data set champion. So someone who is responsible for getting that planet out sort of to publication. So they'll do the lead analysis and write the paper, and this will sort of be like their planet. And then there's going to be lots and lots of future work to do, and that's going to, of course, kind of be open to everyone. But I'm really proud that all of our data set champions are early career researchers. So they're all either PhD students or postdocs. And this is great because they have the time to really dig into this data and get it to where it needs to be. And of course, I think it's also important to promote students and postdocs as they make their way through the first stages of their careers. So yeah, the team is working hard. We're super excited. We're just sort of spinning up our kind of bi-weekly meetings, trying to compare pipeline results. And, a timeline's always tough. We're hoping to get our first results out by the summer. We won't have our first completed data set until the end of this month. So even though we have made a few observations, we don't have a completed data set on any one planet that we can start pushing on. So that'll come in a couple of weeks. So very exciting time, but just at the beginning. So I don't have any big results to share, but maybe I can give you a few hints.
Fantastic. That is so exciting. And just getting the time on the James Webb Space Telescope is a huge achievement in itself. I can't imagine how competitive it is. And look, just a quick change of pace here. Here's a quote, listeners, from Hannah, which I know will astound some of you. It's mind-boggling. Here it is. Quote, "There are more planets than stars in the Milky Way, and Earth-sized exoplanets are the most common," unquote. Now, we know very well that science doesn't always sail smoothly, and we're very happy to put on our propeller heads. You've already challenged us quite a bit. Could you share with us some details of a particular part of your small exoplanet atmospheric research that you're working on right now that's driving you crazy or is astonishingly exciting? Or maybe it's both, Hannah.
Yes. So definitely the most exciting thing in my life right now is the Hot Rock Survey, or I should say my work life right now is the Hot Rock Survey. And it is astonishingly exciting and also driving me crazy. So it's really a mixture of both. I think I've sort of communicated a bit, why it's exciting. We're getting a first look at these planets, going to try to understand on a large scale if these terrestrial worlds can even have atmospheres. But the piece that really keeps me up at night is that the method we're using to do this, as I mentioned, is, the planets are passing behind their host stars. And that means that the secondary eclipse signal has actually never been seen before because we've never had a telescope that could even detect it. Yep. And so what keeps me up at night is the concept of orbital eccentricity, which sounds super boring, but it is truly terrifying. Basically, this is, the idea that, a sort of simple model of planets is that they're on these sort of perfectly circular orbits, but there is actually usually some small amount of eccentricity. And this was sort of the thing that, Kepler figured out back in the day. The problem is that if you have an orbit with enough eccentricity, then just because you see the transit doesn't mean you actually know when the secondary eclipse is going to happen. And, if you don't know by a few seconds or a few minutes, okay, that's fine. We always get time before and after. But if the eccentricity is high enough, you could end up being uncertain by a few hours.
Yep.
And that's too much. You can't ask for, tons and tons of time just to maybe catch something. Or you can, but you need a much better reason. So a lot of work and a lot of, emails to dynamicists and sort of, probability calculations went into trying to make sure that we could actually catch these events. Now, the fun piece I'm going to share with you is we do have already from the program 4 secondary eclipse observations out of what will be a total of 22. And we think we are seeing the dip that we are looking for in all 4 of those observations.
Nice.
But we want to make really, really sure that we are not being tricked by maybe some noise, maybe an unlucky systematic. So this means that we have to comb through all of the auxiliary data that James Webb collects while it observes and see if there's anything that might be tricking us into thinking that this little dip is actually due to something else. So for example, as JWST is settling into its life out in space, it's sort of like a house that creaks a little bit. So there's these sudden, like they call them these mirror tilt events that have been observed to happen. There's nothing wrong with the telescope. This is completely normal. But if one of those little mirror tilt event happens, it just kind of creates a little shift, a little offset in your data. And that's fine. You can correct for it. And this one's actually pretty easy. You can easily check if that has happened. But if you don't check and one of those happens, you might think that there is an eclipse somewhere where there isn't one, or maybe you might think your eclipse is deeper than you think. And, you'd have to be pretty unlucky with the timing, but it's certainly not impossible. So that's a kind of easier one to check for, but there's many, many other little things like that. And, ultimately, we're looking in these secondary eclipses, we're looking for signals at the level of a few tens to hundreds of parts per million. So that is a dip. That signal is about 0.01%.
Whoa.
So it's really, really small. This is not something that was remotely possible before JWST. So we're already kind of like pushing it to the limits of what we can detect. But it's just not an easy signal to pull out. James Webb can certainly do it, but it's, we're not getting these like big, beautiful transit signals that maybe you saw from like the big press releases from JWST. We're looking for itty bitty tiny signals that we're hoping are actually in the data. So very exciting, also very much driving me crazy.
Wow, pushing the envelope. Okay. Look, I've had a look at some of your published papers and I noticed that you wrote a number of them when the COVID pandemic was at its peak back in 2021. And Denmark has been a success story in many ways with its act fast and act with force policy, a bit like ours here in Victoria. Denmark came through relatively unscathed compared with some neighbouring and many comparatively sized countries. How did COVID affect you and your family, and what was the impact on your astrophysics research, and what were the lessons that were learned there?
Yeah, I would say, I'll first just say I was very fortunate that my friends and family came through COVID okay, and everyone's fine and healthy. I actually moved to Denmark in September 2020, so sort of right in the middle of the pandemic, which was, I had like 2 masks on, like barely eating on the plane. It was not the easiest move, but it was much more controlled here in Denmark. There was much more compliance with, if there was a mask mandate in place, everyone wore their mask. When the vaccine became available, everyone voluntarily got their vaccine. And it meant that Denmark was able to sort of open up more quickly and open up more fully. So, even going back to the US sort of some years later, and there's still sort of half people are masking, or there's some small outbreaks, Denmark was able to, I think, quite effectively sort of, lock down hard, but then open up much, much more easily. Now, this is a much smaller country, and there's a lot more trust in government here. So that's definitely something they were able to do. But as far as it affected my research, we were sort of encouraged to limit going into the office. So I had to do a sort of hybrid work from home thing, which was a bit tough at first because I had no furniture. So I would sort of be like sitting on the floor, just hooked into an Ethernet cable, kind of like typing away. But I luckily had already had some research projects that I was kind of finishing up for my thesis. So it was definitely tough to like kind of start collaborations here, even with my coworkers, because I wasn't seeing them. And it's tough to kind of meet people over Zoom, and even tougher to then sort of have those conversations that can really get a kind of collaboration going. Yeah. So I sort of just focused on finishing up some work for my PhD. And I would say I was pretty lucky with I only lost one potential transit observation due to COVID. There was a shutdown at the telescope. And in the greater scheme of things, that's manageable. The one the one upside to observational astronomy is, when a space telescope is taking your data, the space telescope can operate even if you are not able to go into your office. So, because I don't have a lab, I was able to keep working. And sometimes, honestly, just being kind of home with nothing to do when nothing's open, I was like, well, might as well get some research done. So it wasn't too bad, honestly. But I do think in terms of, you asked about lessons learned. I think everyone had a very different kind of COVID experience. And it was definitely a time of sort of thinking a bit more about my colleagues as sort of human beings in their personal lives, just because you're Zooming with people at home and like someone's kid runs by and, it's just sort of, it was having a bit more kind of compassion about, oh, this person didn't respond to my email. And then you get on a Zoom with them and it's like their house is in chaos because, they've been working at home and, their spouse and their kids and their dog is, barking. And, it sort of gave me like, okay, everyone here is a person. Let's give some grace and give some time. And I think a lot of people experience that as well. So I think it's been in some ways positive for the field and for sort of academic life in general.
Yeah, indeed. And look, while we're on the topic of humanity, and it's a good segue here, you've painted the big picture of exoplanet atmospheres. We've looked at your early research and your most current work, and we've gone all sciencey just for a little while. But Hannah, would you like to tell us about some of the things outside your work at DTU Space? What brings you regular experiences of great joy in your life?
Sure. I try to have a sort of rich, full life outside of my work. I think the work-life balance is really important. And it's been a great sort of life experience to live in Denmark. I live in the capital city of Copenhagen. I live here with my partner, who we moved together here from the US. So we're always spending our weekends trying to go somewhere new in the city. There's always kind of art shows that are being put on, usually a concert you can see. There's great restaurants, great bars. So I really like sort of traveling and exploring new places. So it's been so much fun to do that in a new country. And it's also been, sort of so much fun to kind of go around and see, you can just like take a train and be in a different country, in a different city, and coming from somewhere like the US that is so exciting and so novel. So that's kind of what a weekend will look like. I really like to camp and hike and go backpacking. So there's been great opportunities to do that, not in Denmark, but in Norway and in Sweden, which are very nearby. So I've been taking a lot of advantage of that for sort of a little longer kind of week vacation. It's been really rewarding to sort of live somewhere where that's expected and encouraged to take that time to yourself. And so I've really tried to take advantage of that and sort of make sure I incorporate that, for the next stage, whatever I do next. I want to make sure that I honor the life part of the work life.
Fantastic. I'm having a bit of an envy attack here. Thank you.
Oh.
Look, you're teaching, you're mentoring graduates and undergraduates, you're leading your study groups, you're a PI leading an incredibly talented research team, and you have a long history of giving invited talks to colleagues and open talks to the general public. Is outreach an important part of being an astrophysicist?
Yes, I think it's not just an important part, but kind of an integral part to the job. So what I do is basic research, and most of my work is publicly funded through national grants. And so that means that, to some degree, taxpayer dollars go to make this research happen. And that means that you have to give that back to the people, and especially if they're interested, just to sort of make that available. It took me kind of a while to figure out what kind of outreach I like to do. I think a lot of people are really excited about kind of encouraging the next generation of scientists. And I think that is incredibly important, but I have really never liked working with kids. And so I would sort of do a couple of things like that and just be completely exhausted and not in a fun way. And then towards the end of graduate school, I signed up to be a part of this series called the Beacon Hill Lecture Series. And it's basically a set of courses that retired folks can sign up for. So these people are not necessarily scientists or engineers or anything like that in their professional lives, but maybe have always had a personal interest in astronomy. And now they're retired, so they can, take these classes in the middle of the day in Boston. And so I gave an hour lecture on sort of the field of exoplanets. And that was super fun. I loved it. I loved getting questions from these, really interested people who, maybe they're not going to have a second career as an astronomer, but I think they're absolutely, deserving of being reached out to sort of explain what's happening in the current field of astronomy. So I've definitely continued that. There's a similar lecture series here in Denmark called the Folkeuniversitet. So it's like the People's University. So I have given lectures on exoplanets for a sort of astronomy course that anyone in Denmark can sign up for. But again, it's usually generally like retired folks looking to continue learning and continue being curious. And that's been really enjoyable. So I've done more of that kind of outreach after I figured out that, I don't have to go into elementary school classrooms. I can actually, talk to sort of the part of the population that I really enjoy reaching out to. And I think that's just as valuable since, they're the ones actually helping to fund the research. And we should also focus on, people at all stages of their lives trying to learn and being curious.
Excellent. Thank you very much, Hannah. Now, finally, the mic is all yours, and you've got the opportunity now to give us your favourite rant or rave about one of the challenges that we face in science, in equity, in representations of diversity or science denialism. I've got a long list here. Science career paths, your own passion for research, or, as you've hinted at before, our human quest for new knowledge. The microphone's all yours, Hannah.
Thank you. I think I mentioned at the top that I always had all these interests in school before landing in astronomy. And one of them is that I've always loved to read, and I love literature and even a little bit of writing to some extent, but mostly reading. And as I've gone further and further in astronomy, I find myself thinking more and more about sort of narrative and stories, and how actually just as important of science research is the communication of that research. And there's stories about our research, there's stories about ourselves, and being sort of aware of where you are in a story or how a story has formed about your research, about your career, I think is something that's been really, I've really found it powerful to think about recently. So I'll give kind of a few examples, or I'll give two examples. For example, my career story changed a lot when I got this Hot Rocks program accepted to JWST. And, it's very good to keep a positive attitude. And this is a really great story to tell. I studied these terrestrial exoplanets as a grad student, kind of struggled, and then, finally made it to this big program that's going to answer some of these questions that I am genuinely excited about. But what's kind of hidden in that story are a lot of rejections and a lot of setbacks and really some wavering on whether or not I wanted to continue even working in astronomy or not. And, my story from like 2 years ago was a little bit meandering, a little bit lost in a way. And then suddenly this one sort of lucky thing happens, and that really turns the whole thing around. And I think it's important to sort of be aware of how that story is changing. One, because it can be, in one sense, like, keep going, it can change. But in another, to sort of remember that, like, this was not, predetermined, that there was no sort of steady march towards where I am today. There was a lot of uncertainty. And I think there was just as good a chance that my program wouldn't be accepted, and maybe I would have kept going and maybe not, and who knows. And that's kind of, you have to sort of take these things that the universe kind of throws at you.
Yeah.
But I think it's also important too to realize that science is also about storytelling.
Yep.
And I'll give one last example. This is sort of about a paper I published in 2022, and I will give a nickname to this system. It's called the K23 system, and it has 3 planets, and I'll call these the 3 bears. And the first planet closest to the sun, this is like the big bear. It's a sub-Neptune. It's larger, more massive than the Earth. It's puffier. And then there's kind of sort of further out from that, there's a slightly smaller planet, maybe sort of between a sub-Neptune and a rocky planet in terms of size and mass. And then farther out, just kissing the habitable zone of this system, was this little planet that we thought was terrestrial. Maybe this is the perfect planet for life, right in the Goldilocks zone, Goldilocks and 3 bears. Okay, so when I was first looking at this system, I thought, okay, this is cool. We have 3 planets. They're around a common host star. So I can kind of put all this data together, use our models of atmospheric mass loss and evolution, and just sort of explain the story that I was clearly seeing with these 3 planets, one maybe perfectly in the habitable zone. But while I was putting together the observations and models from my colleagues and sort of digging into the literature, the story was not fitting together. There kept being these pieces that didn't make sense. And instead of just ignoring those, I kind of tried to bring those in and see what was happening. And what I ended up with is actually a very different story, where it actually seems that maybe these planets formed farther out than we currently see them and migrated inwards, which means that outer planet that I thought was my, just right rocky planet in the habitable zone, I'm now thinking actually it's just a sort of much smaller version of a sub-Neptune, something that has a puffier atmosphere than we expect. And the best part of this story is that it needs an epilogue. So now there's more work to do to try to test that hypothesis, see what's actually going on. But, just like with this system and with, sort of our lives and really anything that happens, just sort of learning through that scientific process to be open to maybe the story is not going the way you think it's going to go. And that doesn't mean it has to be worse. It just means it can be different, and sort of being open to that and open to a maybe even more exciting outcome, I think is really important in science and in our careers, and also in life. That's what I've been thinking about recently.
Fantastic, and you are indeed a storyteller. You've combined art, science, literature, and storytelling all in one here for the last hour with us, Hannah. Look, just before we go, is there anything else we should watch out for in the near future? What are you keeping your eye on?
Yeah, so please stay tuned for results from the Hot Rock survey. But I also think there's a lot of really interesting research. Definitely anything for exoplanets coming out of James Webb is going to be really exciting. But I also just want to make a quick plug to don't lose faith in your ground-based telescopes. There is so much interesting work coming out of ground-based telescopes, from high-resolution spectrographs. This is a whole other kind of technique for trying to detect atmospheres that I didn't even get a chance to talk about. But we are trying to build these next-generation ground-based telescopes. And these really they're not competing with JWST. They're really complementary and they're really necessary. There's some things that you can do from the ground, make these very, very technically sort of finicky instruments that you need to constantly tune that you just can't do from space. And so I don't want people to think that, just because we've put up James Webb, we can forget about all these amazing ground-based telescopes that people work on, maintain, and they are still producing really exciting science. So I would say don't lose faith in your ground-based observations.
Fantastic, and there's some amazing instruments being constructed as we speak. Okay, well, thank you so much, Dr. Hannah Diamond Lowe. On behalf of all of our listeners, and especially from me, it's been really exciting to be speaking with you way over there in Denmark, chilly as it is and hot as it is here. Thank you especially for your time and your amazing schedule and the pressures to analyse all that beautiful hot rocks data that a JWST is going to be, or is and will be beaming down to you. And good luck with your next adventures, your research, your wonderful weekends that you're having, and all your future travels. And our listeners can tune in to the work that the Exoplanets group do. They can see the people and their research. It's all at exoplanets.dk. May your career continue to be out of this world. Thank you, Hannah.
Oh, thank you so much. This was so much fun.
Excellent.
Bye-bye.
And remember, Astrophiz is free and unsponsored. But we always recommend that you check out Dr. Ian Musgrave's Astroblogger website to find out what's up in the night sky. See you in 2 weeks. Keep looking up. Radio 1.